Welcome to our deep dive into the 5 essential concepts every embedded developer should master. Whether you're just starting out or looking to sharpen your skills, understanding these core principles will set you apart in the world of embedded systems. Today, we'll break down each concept, explore practical examples, and highlight why these fundamentals are crucial for building reliable and efficient hardware solutions. Let's embark on this journey to mastering embedded development, starting with the basics and moving step by step into more advanced territory. First concept is memory map I/O and register programming. In embedded systems, microcontrollers expose hardware through memory map registers. This means that to control hardware, you need to interact directly with these registers. Mastering this area involves understanding bit masking, shifting, and logical operations. It's also crucial to become comfortable reading datasheets and working with volatile read-write registers. These skills form the foundation for any hardware interaction, making them indispensable for embedded developers. Let's look at a practical example of register programming. Imagine you need to toggle an LED or read a sensor value. This often requires setting or clearing specific bits in a control register. By using bit masking and shifting, you can manipulate only the bits you need without affecting others. Reading and understanding the microcontroller's datasheet is essential here, as it tells you exactly which registers to use and how to configure them. This hands-on approach is what makes embedded development both challenging and rewarding. Moving on to interrupts and concurrency, this is where things can get tricky. Interrupt service routines, or ISRs, are special functions that run in response to hardware events. If not managed properly, they can disrupt your program's logic and lead to hard-to-find bugs. To master this area, focus on writing fast, minimal ISRs, preventing race conditions, and carefully prioritizing and nesting interrupts. These practices ensure your system remains responsive and reliable, even under heavy workloads. See how to manage ISRs in practice. A well-designed ISR should execute quickly and avoid complex logic. This minimizes the risk of interrupting other critical tasks. Preventing race conditions is also vital. Use synchronization techniques to ensure shared resources aren't accessed simultaneously by multiple routines. By prioritizing interrupts and nesting them only when necessary, you can maintain system stability and prevent unexpected behavior. These strategies are key to building robust embedded applications. Next, let's talk about memory layout, an often overlooked but critical aspect of embedded development. Embedded systems typically have limited memory, so understanding how memory is organized is essential. This includes knowing about the BSS and data segments as well as the startup code that initializes your system. Reading and modifying linker scripts allows you to control memory allocation, while keeping stack and heap usage under control prevents crashes and unpredictable behavior. Delving deeper into memory management, it's important to distinguish between the stack, heap, and various memory segments. The stack is used for function calls and local variables, while the heap is for dynamic memory allocation. Mismanaging either can quickly exhaust your system's resources. By understanding how your code and data are laid out in memory, you can optimize usage and avoid common pitfalls like stack overflows or memory leaks. This foundational knowledge is vital for any embedded developer. Let's move on to clock systems and timing. The clock configuration in your embedded system affects every peripheral and determines overall power usage. Mastering this area means understanding clock trees, prescalers, and how they influence peripheral timing for interfaces like UART, SPI, and timers. Balancing frequency and power consumption is a constant trade-off, especially in battery-powered devices. By tuning your clock system, you can achieve the right balance between performance and efficiency. Practice configuring your system's clock involves more than just setting a frequency. You'll need to consider how different peripherals interact and how timing affects communication protocols. For example, UART and SPI require precise timing to function correctly. Adjusting prescalers can help you fine-tune performance while keeping power consumption in check. Understanding these trade-offs is key to designing systems that are both fast and energy efficient. Fifth key concept is GPIO and electrical setup. General purpose input-output, GPIO pins are the primary way embedded systems interact with the outside world. Mastering GPIO means understanding pull-up, pull-down, and open-drain modes, as well as handling button debalancing in both hardware and software. It's also important to know the signal requirements for peripherals like SPI and UART. While development environments can assist, a strong foundation in these basics is essential for effective debugging and hardware control. Debugging GPIO issues can be challenging, especially when dealing with noisy signals or unexpected behavior. Understanding the electrical characteristics of your system helps you diagnose problems quickly. For example, knowing when to use pull-up or pull-down resistors can prevent floating inputs and erratic readings. Additionally, handling debalancing in software ensures reliable button presses. These troubleshooting skills are invaluable for any embedded developer working with real hardware. Let's pause for a moment to define memory mapped I/O in embedded systems. This concept refers to the technique of mapping hardware registers into the address space of the processor. This allows software to interact with hardware simply by reading and writing to specific memory addresses. It's a fundamental concept that underpins most microcontroller architectures, making it essential for low-level hardware control. Interrupts are signals that temporarily halt the normal execution of a program to allow the processor to respond to urgent events. This mechanism is crucial for real-time responsiveness in embedded systems. By mastering interrupts, developers can ensure their applications react promptly to hardware events, such as button presses or sensor readings, without missing critical data. Memory layout refers to how different sections of a program, such as code, data, and stack, are arranged in the memory of an embedded system. Understanding this layout is vital for optimizing memory usage and ensuring reliable operation, especially in resource-constrained environments. Developers must be familiar with segments like BSS data and the stack to avoid common pitfalls. Clock systems and embedded devices provide the timing signals that synchronize operations across the entire system. The configuration of these clocks affects everything from peripheral communication to power consumption. By understanding clock trees and prescalers, developers can fine-tune system performance and efficiency, which is especially important for battery-powered applications. GPIO, or General Purpose Input-Output, refers to the configurable pins on a microcontroller that can be used for input or output operations. Mastering GPIO configuration is essential for interfacing with sensors, actuators, and other peripherals. Understanding electrical modes and signal requirements ensures reliable hardware communication. Masking and shifting are fundamental techniques for manipulating individual bits within a register. By applying a mask, you can isolate or modify specific bits without affecting others. Shifting allows you to move bits left or right, which is useful for setting or clearing flags in control registers. These operations are at the heart of efficient hardware control in embedded systems. Key skill for embedded developers is the ability to read and interpret datasheets. These documents provide detailed information about microcontroller features, register maps, and electrical characteristics. By mastering datasheet navigation, you can quickly find the information needed to configure hardware and troubleshoot issues, making you a more effective developer. In embedded programming, volatile registers are those that can change unexpectedly, often due to hardware events. Declaring a variable as volatile tells the compiler not to optimize accesses to it, ensuring that your code always reads the latest value. This is especially important when working with hardware registers that can be modified outside the normal program flow. Race conditions occur when multiple processes or interrupts try to access shared resources simultaneously, leading to unpredictable results. Preventing race conditions is crucial in embedded systems where timing is often critical. Techniques like disabling interrupts during critical sections or using atomic operations can help maintain data integrity and system stability. Not all interrupts are created equal. Some events are more urgent than others, so embedded systems often support interrupt prioritization and nesting. By assigning priorities, you ensure that the most critical tasks are handled first. However, excessive nesting can lead to stack overflows and increased complexity, so use this feature judiciously. Linker scripts define how your program's code and data are placed in memory. By customizing linker scripts, you can optimize memory usage and ensure that critical sections are placed in fast or protected memory regions. This level of control is especially important in systems with limited resources or strict timing requirements. Careful management of the stack and heap is essential in embedded systems. The stack is used for function calls and local variables, while the heap is for dynamic memory allocation. Monitoring usage and setting appropriate limits prevents overflows and memory leaks, which can cause system crashes or unpredictable behavior. A clock tree is the hierarchical structure that distributes clock signals throughout an embedded system. Understanding how to configure and optimize the clock tree is vital for ensuring that all peripherals receive the correct timing signals. This knowledge helps you balance performance and power consumption effectively. Each peripheral in an embedded system such as UART or SPI has specific timing requirements. Configuring these correctly ensures reliable communication and operation. By mastering peripheral timing, you can avoid data loss, communication errors, and ensure your system runs smoothly under all conditions. One of the most important trade-offs in embedded design is between power consumption and performance. Higher clock speeds improve performance but drain more power. By carefully selecting clock frequencies and optimizing code, you can achieve the right balance for your application, especially in battery-powered devices. GPIO pins can be configured in various modes, including pull-up, pull-down, and open drain. Each mode serves a specific purpose, such as preventing floating inputs or enabling wired-AND connections. Understanding when and how to use each mode is key to reliable hardware interfacing. Mechanical buttons often produce noisy signals when pressed or released, a phenomenon known as bouncing. Debouncing techniques implemented in hardware or software filter out these unwanted transitions to ensure that each button press is registered accurately. Mastering debouncing is essential for user-friendly interfaces. Different peripherals such as SPI and UART have unique signal requirements. Understanding these needs ensures proper communication between devices. For example, SPI requires specific clock and data lines, while UART needs precise baud rate settings. Mastering these details allows you to connect and debug a wide range of hardware components. While modern IDEs offer powerful debugging tools, a strong foundation in embedded basics is irreplaceable. Understanding how hardware and software interact at a low level helps you diagnose and fix issues that automated tools might miss. This expertise is what sets great embedded developers apart from the rest.